Folks, here's the work that you did last lesson and partly for homework, I guess. Comes straight from the PowerPoint presentation Mathematical Induction 3, which is on the Google Drive. I have altered a little bit at the end, so your printouts, the answers might be slightly different right at the end, but I've actually simplified it. Let's have a look at this first one. Remember, of course, we always go through that first stage of proving true for n equal to 1. So we go through that left-hand side equals, that it's the first term, right-hand side, and we substitute 1 into that one, and we get a 1 which is equal to the left-hand side. And so we can say true for n equal to 1. We assume true for n equal to k, so all we do is substitute a k for the n, and then we add the k plus 1th term. Here's where lots of people make a mistake. They are fine on this side. They say there's the k squared, and then we have the extra term where k plus 1 is instead of n. So they'll have plus k plus 1 squared. But then where they make the error is that they jump the gun and they put k plus 1 instead of n there. So they'll have k plus 1, k plus 1, plus 1, etc. here, which actually is going straight to the assumption that it's true. Now, the only way you can do it, because you're adding k plus 1 squared to that side, the k plus 1th term, you're going to do that principle of equations where what you do to one side you do to the other. So we're just going to add k plus 1 squared onto that side. Now, what we hope is that when we simplify this, it reduces to the formula, that formula with k plus 1 instead of n. It's a game of hope, very satisfying when it works out, though. So, we're just going to go through normal mathematical principles. I've done this in rough. Please understand that this is not part of the question. So, and especially, you don't have to draw that ridiculous drawing of the dog. That's just me being stupid. You do this on a separate paper. You don't put it as part of the proof. And the person marking doesn't have to see this. So I've taken that original formula, I put k plus 1 instead of n there, and then I've simplified it out to there. I'm not going to go any further because I can see this is turning into a cubic. Now I need to factorize in the end, 1, 2, 3 factors. So it would be a backward step to multiply everything out if I can't take out a common factor first. So I'm going to find a common denominator. There we are. So there's your k plus 1 squared. Now 6 times k plus 1 squared over 6. Now have a look at this at this stage. We have a common denominator. There are two terms, two terms, and k plus 1 is a common denominator. Common factor. I don't know why I'm talking about common denominator now. All right, so we take out a common factor of k plus 1. And then what we're left with is that k times 2k plus 1, giving us 2k squared plus k, and that's 6 times the remaining k plus 1, which is 6k plus 6. Now I can simplify within the brackets, and I'm now going to factorize that quadratic. And I see that it is in fact that quadratic. If it wasn't, then there'd be a problem with my proof. There it is there. Now I need to take the extra step now to show that it is that formula with k plus 1 instead of n. So I'm going to write that next. There it is there. Now, what I'm going to do next is I'm going to say therefore true for n equal to k plus 1, and I'm going to remove this. So you'll see there we are. That's what your proof should look like. Strictly speaking, in the really rigorous maths, they would write, therefore, based on the fact that it's true for n equal to k, comma, true for n equal to k plus 1. And that's what I did originally, but I've taken out all that confusing stuff. And from there, we go straight to, therefore, by mathematical induction, it is true for all n element of natural numbers. Let's have a look at the next one. Much the same sort of thing. There is another mathematical induction. So we're going to take the left-hand side, take the first term, right-hand side, and substitute in the 1 for the n equal to 1. And we obtain 2, which is the same as the left-hand side. Now we do that assumption that it's true for n equal to k. And there it is. Now, once again, we add k plus 1th term, which means 3 times k plus 1 minus 1. 3 times k plus 1 minus 1. Not, and then on this side we add the same. We don't substitute k plus 1 into there. That's where we hope to get to. But we're going to do that mathematical principle, do the same to both sides. So there's the k plus 1th term, 3 times k plus 1 minus 1. There it is. And we add the same to that side. Our rough work, well, we know that we're going to have to end up with a k plus 1 instead of the n there, and a k plus 1 instead of the n there. There we are, like that. And if I multiply that out by rough work, which you don't put into your actual proof, we end up with that. So let's hope that that's the case. We're going to include this into the fraction. There we are. I've done a bit of mathematical license and simplify a little bit with that red bracket there, of course. Sorry, sometimes I wiggle the mouse about because the mouse keeps disappearing when I'm doing this video. Okay, and I'll simplify to the next line, and I say, well, there's a quadratic. Hopefully it'll factorize that. If not, there's something wrong with the proof, or the original statement isn't true. But in fact, it does factorize to the right thing. We then write it in that form. And we can take out the rough. We now just have the final words, true for n equal to k plus 1, and the final statement about it being true for all n element of natural numbers. Right, here's one with exponents. So we're going to take for n equal to 1, and we take just the first term. And then we're going to substitute 1 for n in the right-hand side. And we see it also comes out as 2, which is equal to the left-hand side. So therefore, true for n equal to 1. And we now assume true for n equal to k. Now we're going to add the k plus 1th term to both sides. Note that that'll therefore be plus 2 to the k plus 1 in there, and plus 2 to the k plus 1 there. Now what we hope that we're going to get is 2 to the k plus 1. Notice there's, instead of n, k plus 1, plus 1 minus 2. That's what we hope to get, which if I simplify comes to there. Now, be aware of, we have terms that are, often we have like terms with these exponent inductions. If you have a look there, we have a 2 to the k plus 1. There we have a 2 to the k plus 1, which means we have 2 of them. So there's 2 times 2 to the k plus 1. You could have grouped these two and then taken out a common factor of 2 to the k plus 1, and you'll end up with 1 plus 1 in the brackets, which also gives you your 2. So there we are there. Now, we're not quite there yet because this is just 2 to the, and this is 2 times. So this is 2 to the 1, so I'm going to add it to the exponent there. Now, if you have a look there, we now have what we need. And we write there, true for n equal to k plus 1, and then our final statement. Right, now this looks a bit heavier, but let's just be confident, go through it, treat it the same way. Left-hand side, n equal to 1, so it's the first term, 1. Right-hand side, substitute 1 in for the n, and we'll get 1. Strictly speaking, I suppose I should put the equals 1 there. All right, so true for n equal to 1. Assume true for n equal to k. So there we are. We repeat that statement with k instead of n. Now we add the k plus 1th term. So it's plus k plus 1 cubed and plus k plus 1 cubed. And I hope I'm going to end up with some factorizing along the way. We'll see. Now that's cubed. If it was squared, that would be useful because, no, I wouldn't be. I was going to say I could take it into the bracket, but I wouldn't be able to because then it would be subtracting, and then that's a very different matter. But what I'm going to do is I'm going to allocate that squared to there and there just to simplify, so that then this can go into the fraction. This can't go into the fraction as long as that's all squared like that. So I need that. There we are, k plus 1 instead of k, instead of n. And so we need to end up with that. So let's work at this. There we are. I've squared, and now I can include that into the fraction. Oh yes, we have a k plus 1 squared common. There's my k plus 1 squared. So I hope what's left is k plus 2 squared. So we take out a k plus 1 squared, and we're left with k squared plus 4 into the remaining k plus 1. Give me that. And absolutely, that there is k plus 2 squared, and we've got to what we want. But we must write that level to show that it's k plus 1 instead of n. There we are. So therefore, true for n equal to k plus 1, based on the fact that it's true for n equal to k, and therefore the final statement. Right, one of these divisibility proofs. So much the same thing. I'm going to take for n equal to 1. I'm going to see it comes out as 6, and that's divisible by 6, therefore true for n equal to 1. Assume true for n equal to k, which means therefore k plus 1, k plus 2 will be divisible by 6. Now we can't say add the k plus 1th term because that's not an equation. So instead we say for n equal to k plus 1, we have that, which is k plus 1, k plus 1, k plus 1 in those three places. I simplify it to there. And what I've done, because I see I need a k plus 1, k plus 1, k plus 2, so that I can use that fact there, I can see that there's the k plus 1, k plus 2, k plus 1, k plus 2. So therefore, let's multiply by the k and then plus by the 3. So there, that's the part in blue, and that is divisible by 6 by that assumption. So we're left with the green, and we have to reason that the green is divisible by 6. Well, it's already divisible by 3, the green is. So we need to show that it's divisible by 2. Well, if you have a look, these are consecutive numbers. And if you have consecutive numbers, one of them must be an even number. Right, so we established that that term is divisible by 6. And then we reason, since one of those two must be even, because they're consecutive numbers, that there, the green, must be divisible by 3 times 2, 6. Therefore, the whole expression is divisible by 6. So therefore, we can say true for n equal to k plus 1. And our final statement.